Recordings, rolling. It is Tuesday, January 14th. All right, we're going to do this rotational inertia lab today. I've got this set up over here. So here's how we're going to do this one. I'm going to just model this up in front of the class. I'll get a couple volunteers to take times with the stopwatch. Actually, I think I get 3 volunteers with the stopwatch because you guys got some stopwatches, right? Because this one is labs. I mean, it's got popsicle sticks are easy to break, and it's a little bit involved in terms of the table. So sometimes students get kind of lost. But if I'm up here guiding, like, okay, here's step by step by step, then makes a lot more sense. The data looks really nice. Everything clicks together. That this graph looks like really perfectly exactly as it should. Right. So that's the way we do this. Right. So what we're trying to figure out is what's the rotational inertia of this pipe system about its central vertical axis. So I have this rigged up over here, and I do have this camera trained right on that system. So for the recording, I'm going to flip camera screens at some point. Like right now, it's on the stock cam, but I'm going to flip to that. If you're in class, you guys see this camera right here. This point right is that. That's it. Looks like this. So I got this pipe system. It's a low friction system, and it can twist around the central vertical axis. Now, if it was rotating about any different axis, it would be a different rotational inertia, right? Right. So here, let's see if I can show this with, right, this right here. Okay, so you guys remember this idea of rotational inertia? You guys remember those 2 sticks that was passed around? They're over there by that fire blanket box right now, if you want to get your hands on those. Also, I still got this bicycle wheel that I had as a demo yesterday, or something like that. Right. But see this rotational inertia table? Right, these are all calculus-derived values for these shapes, but notice they're all about some defined axis. Like, for example, the solid cylinder is about this axis goes right through the center, which if you turn that vertical, that would actually be a turntable, wouldn't it? Like a cylindrical look on turntable. Okay? Or what if you spin a coin? Did I do this yesterday? Did I take a quarter and like spin it on the side? Okay. Here's the rotational inertia associated with the spinning coin. And it does have to be a thin coin. If it gets too thick, then it's a little more complicated. Okay? This basketball one we've been using. Notice this is only if you're, say, spinning it on your finger. Oh, yeah, okay.
So the M's are capital M, is still mass, or is that?
Yeah, M's mass. Yeah, yeah. So, like, if you know the mass of the basketball, that would go in for this M. If you know the radial size of the basketball, it goes for R. So M is mass, R is radius. Yeah.
Or if it has a greater rotational inertia, it's been faster.
Okay, guys, greater rotational inertia means more. Okay, well, what is inertia? Isn't inertia resistance to change in motion? Right? So if it starts from rest, if something has more rotational inertia, is it easier or more difficult to get it rotating? More difficult. Yeah. Okay. And then once it is rotating, oh, if it has more rotational inertia, does that make it easier or more difficult to bring to a stop if you bring it to a stop? Yeah, if it has more rotational inertia, it's also more difficult to bring it to a stop. It's harder to get it spinning. It's also harder to stop it if it has more inertia, right? Because that's what inertia is. It's tendency to keep doing what it's doing, right? In a linear sense, it was just how much mass. It's like more massive, it's harder to get it going, and it's harder to stop it. In its rotational sense, it's how is that mass distributed, okay? Okay. Something to do with thinking. MR squared, and then so back to it. Fix this. Okay. All right. So thank you. All right. So you guys good so far? Okay. All right. All right. So you have to have a defined axis. Let me flip a few because here, like if this basketball was rolling across the floor, you guys remember it's not actually rotating about its center mass. It's rotating about this point all the way at the bottom. Okay. That's a different type of inertia. So if you were to start pushing a ball across the floor to get it rolling, or if it was rolling towards you and you were to stop it, the rotational inertia you would feel effectively would be not 2/3 mr squared, but 5/3 mr squared because ball is rolling across the floor. It's a little parallel axis theorem going on, okay? Which AP is just bringing back this year. This parallel axis theorem. They haven't done this for a few years. Okay, okay. You guys good so far? Okay. All right. So let's go back here. All right. So here's the setup today. All right. Again, low friction. All right. Let's get a good forest for the trees picture of exactly what's going on so we can make sense of this. Okay. Because you guys got a lab table in front of you that we're going to do. Right, hold on. All right. So I got the system. Notice this dashed line right through the vertical. That's the point that it's going to spin about. You guys see it. You guys can see it in class. See kind of like spin about this point right here. Like that. Okay. All right. And then how are we going to get it spinning? Well, I'm going to take a lab weight represented by this point down here. So I got a whole box of lab weights. Maybe that could be an independent variable, sort of. I could switch out different lab weights throughout the day, right? Throughout the class period. This is going to provide different weights, which is going to be some tension in the string. Right now, that's a little thing we have to take care of too. Right? Actually, let's talk about that a little bit, guys. Is the tension in the string, does that exactly match the weight? No, right. Now, what if it was at rest? Actually, the fact that it's falling really slowly, it's going to be really, really close. I've seen sometimes AP even forgets that detail. I've seen them in there in the scoring rubrics. And it's like, you forgot that. Okay. Guys, is the tension going to be a little bit less than or a little bit more than the weight?
Well,
A little bit less. Okay. Because as this way, if I let this go, starting from rest, this is going to accelerate down. Okay. And anyway, we'll get. You guys remember tension in an elevator cable? It's m times g plus or minus a, depending on which way it's accelerating. This is going to be the m times g minus a part, right? You might have to derive that. Well, maybe they'll show up as a derivation by the end of class, right? So part of, right? Okay. Anyway, there's a tension in the string that's providing a force at this small radial distance. You guys see this central vertical pipe has like some radial size. I think it's about 1 centimeter. I can double check that. Okay. But that's going to provide it. Guys, what is this R times this tension F that creates a, what's that called in physics? Torque. A torque, right? Which gets this whole thing rotating. Okay. Now, as this lab weight's falling, or maybe I ask you guys, is it accelerating? Yeah, which is one reason, by the way, that the tension's a little bit less than the weight. Right? Not too much different, but a little bit. Right? Okay. Which means, is this pipe system going to speed up spinning? It will have an angular acceleration. Yeah. Right. In fact, I remember the connection between linear acceleration of this lab weight falling straight down and angular acceleration, something rotating. You guys remember A equals alpha times R? That was just turntable physics, right? Right. Okay, right. So I remember that. Right, so I think we can put this all together and at the end figure out what is the rotational inertia of this pipe system. You guys have a graph set up. Is this one right here? See tau versus alpha? Okay. Now, guys, what's the formula you guys know that has tau and alpha in it? Like torque and angular acceleration. It's a real short formula. It goes what equals what times what. It's analogous to F equals ma. You guys remember F equals ma? Okay. Instead of force, it's torque. Instead of A, it's alpha. And instead of M, rotational inertia. Okay. This goes torque equals rotational inertia times angular acceleration. Tau equals I times alpha. Okay. That's how we're okay. So guys, when you make this graph, which you're going to do today, right? What property of this graph is going to answer the question? What's the rotational inertia? What property of that graph? The slope. Yeah, the slope. Right? Can you guys see that? Got y-axis versus x-axis. It's like y equals mx. The slope is the answer to the question we're trying to find. Okay, you guys get that? Okay. Force matrice here. All right, so I think you guys have a lab table that looks a lot like this. So we go piece by piece. Some of these you can measure like, or well, first I'm going to guide you guys along here. Like you can measure this radial size of the central axis. You can measure all these things. Right? Some of these you're going to calculate. Like what's this linear acceleration? Bet you have to go back to kinematic for that. Right, what's this angular acceleration? Connect to like the turntable type of. Okay. All right. Got all this elevator physics going on here. And at the end, we'll be able to get this rotational inertia of the system. Right? That's it. All right. Questions so far about the premise, kind of what we're doing? All right. Some more details here. I want to get an estimate, but before we even collect any data with this, I want to get an estimate using a completely different method. And then when we get the answer, we'll go back to the beginning. Okay. You guys see these two down here at the bottom left? Right about the center or right about the end? You guys see those? All right. Let's add that because if I go back to this, that does look a lot like these arms right here. Looks a lot like those. Okay? And the central vertical axis might provide a little bit more rotational inertia, but almost all of it's going to be due to these arms swinging around. Okay? Okay. So if I know the mass and the length of those, maybe I could use either one of these. And actually, if you know one of these in the bottom left, you can use parallel axis theorem to derive the other. Okay. Some do with ml squared and then a factor in the front. Okay. Okay. All right. We'll get a number, and then we'll do this whole lab properly with the table in front of you guys, and we'll see what happens. All right. So let's see what I want to do here. Right. All right. We're going to measure how about this? What's the length of one of these pipe arms, like from here to here? You guys got that? Okay. All right. So if you watch this video at home, I'm going to do this. Actually, I can just pop it apart right here. Okay. So here's one of the pipe arms. I just pop this off. Okay. I'm going to assume it's uniform mass. Okay. All right. What's the length of this thing and what's the mass of this thing? Right. Because we're going to use to figure out one method. Okay. This looks like, let's see, what is that? 61.5 centimeters long. Is it? maybe I'll jot that down. Right. So one of these arms, sketch a quick picture here. Right. So it's like this T shape. Oops. Oh, okay. That's should use a ruler. Try this again. All right. So I got this T shape. Right. This arm right here, I got what I'll say R for a radius or something. Right? That was 0.615 meters. Right. Now, if I know its mass, then I could go to that rotational inertia table and I could really quickly pop this together if I know the mass. Okay. Now the mass I'm going to here, let me try this. I'm gonna switch screens. If you're watching this video, switch over here. Okay. So I should have this camera here, just so everybody knows. This camera should be trained on this area. Okay. I'm going to use that seesaw method that you guys just used back on Thursday to figure out what is the mass. Okay. Can you guys see this sort of? Okay. Notice that here, I got this was my fulcrum point. Everybody see this fulcrum point? Here's my seesaw lever, and it's balanced right on the 50 centimeter mark. Okay, so this is look, it's just really tenuous balance. You guys see that? Okay. I've got some known lab weights, like this one's 100 grams right here. Okay, and then I have maybe some unknown mass right here. Gonna do exactly what you guys just did back on Thursday. Okay, seesaw method. Figure out what's the mass of this thing. Okay, so all I have to do is put these down until they balance, record what are the locations, and then do a calculation. Ooh, looks like. Let's see. Right there, really tenuous balance right there, about there. Okay, so see where are these? This is at the, let's see. All right, so this radial arm right here, I'm looking at 10, 20, 28 centimeters. See 28 centimeters there, and over here I see 10, 20, 30, 41. Okay, so you got 28 versus 41 centimeters. You guys see that? Okay, 28 versus 41. Okay, 28 versus 41. All right. Let's go back over here. Right. So, so if the torque on the left, minus the torque on the right equals 0, so torque left equals torque right. Okay. I had at 28 centimeters was some unknown mass I'm solving for times gravity field. Okay. And on the right side, what did I say? It was 41 centimeters. Was the arm? So 41 centimeters. Okay. There was a known mass of 100 grams. 100 grams. And that was in Earth gravity. Now, Earth gravity matter, so it would still balance the same on Mars. Right? So far. Okay. So what's the mass of that arm? You guys see that? I'm about to figure out what's the mass of that arm. Okay. So all I do is say, well, the right torque was at 41 centimeters was 100-gram lab mass. Right? Earth's gravity cancels out the sides, take care of that. Then divide by 28 centimeters from the pivot point on the other side, right? And that gives me 146. Yeah, so I tried this before school today. I was getting about the same number, about 140 some grams, just to call it, right? 100. Yeah, let's use that number, 146 grams. That's pretty close to what I got earlier today. Anyway, okay. So this, just the mass of that arm, is 141, or what's sorry, 146 grams. Right? Grams. Okay. Now, maybe I should put that in kilograms. Guys, how many kilograms is that?
0.146.
Aha, there you go. 0.146 kilograms. Okay. So now I have this distance in meters and this mass in kilograms. Oh, yeah.
Do we put those torques down for the torque in them?
No. Okay, guys, these numbers don't go on your lab page yet. This is just a preliminary thing, just to figure out. I want to figure out what's the rotational inertia of the system using a different method. Okay, and then we'll do the proper lab, right? And then we'll compare these numbers and see how close they are. Right? You see that? Right. So I got this mass, this radial size. Okay. Now, if I go back to this right here, right, that's one of these arms like this. You guys see 1/3 ml squared? You see that? 1/3 ml squared? All right. Let's try that. So if I do 1/3 times the mass of 0.146 kilograms times this length is 0.615 meters and squared, 1/3 ml squared. Okay. That's okay. Now, a lot of these numbers are going to be small today because SI units are in kilograms and meters. And, well, we're working with the number smaller than a kilogram and smaller than a meter. Okay. So that's okay that the numbers are small. You see 0.018 something. Okay, now that's just this arm right here. Okay, so just this arm has I of 0.018 kilogram meter squared. The unit is kilogram meter squared. Right? That's just that arm. Right? Now, I bet this other arm on the other side is probably the same. Yeah. Guys, you guys think this other arm on the other side is the probably the same? Yeah. Okay. The equation I just used is this one right here. See 1/3 ml squared? Okay. Because that is one arm going around. Okay. Okay. Now the fact that there's another arm on the other side, can I just say times two? Right. Right. Uh, Also, there was a central vertical axis that has a really small radius. It's like radius of about a centimeter. So maybe that adds a little bit. So maybe this could be sort of an underestimate. If I'm just focused on the arms, say, well, that's probably the vast majority of the rotational inertia. It's probably just those arms. So I'm going to say this times two. And say, well, it's probably at least this much. So I'm going to guess I for the whole system is at least 0.0368, I'll call it 0.037. That's kilogram meter squared. Okay, kilogram meter squared, 0.037. Okay, guess that. Now, just to show you guys that this is consistent with maybe the one right next to it. You can see the one right next to it could be the entire arm system above, right? And this is 1/12 ml squared. You guys see that? 1/12 ml squared. Okay, so let's see, that would be probably twice as long and also twice as massive as the numbers for a single arm, right? And then 1/12. Let's see if that also works. 1/12 ml squared, right? So if I do 1/12, oops, 1/12, and then m, now it'd be twice the mass before, so 2 times 0.146, and then the L, but it'd be twice of this, right? So 2 times 0.615, and then that's all being squared, right? All right. If physics is self-consistent, it should be also this number, the same number. Okay, let's see if it is. Yeah, same thing, exact same thing. Is it? Okay, so what he's looking at, right? Okay, are we good? Right. Right. So I think when we do this lab, we're probably gonna get something a little bit bigger than that, maybe like 0.04 something, maybe. Okay. Okay, guys think? All right, let's see. Let's see. All right, so you guys have this table in front of you, right? Really similar to the table I showed on this presentation. We got torque versus angular acceleration, and then here's the end goal is to find this I. Okay, guys, okay. On your desk also, I put this quarter page I printed up a while ago. You guys know this one, AP style write-up? Right. Let's do one of these because this is good practice. We haven't done it in a few weeks here. Okay. So here, review with you guys here. So question, no, the question I went ahead and wrote right here. Okay, what is the rotational inertia of the apparatus about its central vertical axis? Boom. There's your question. Right. So everybody's got the question. Right. Right. Now, as we go along today, here, a lot of times I'll just be grabbing numbers up here. You know, there'll be some time for the weight to fall and things to play out. In the background, go ahead and do this write-up on the back of the page. There's a reason I gave you guys a page that looks like this, and it's blank on the other side. You see it's blank on the other side? That's how you can do this 5-part write-up. You guys conveniently have this quarter page on your desk pod so that you can reference it. Measuring equipment. As we go along today, think, what variables are we measuring? And maybe I should make some note of that to communicate to, say, an AP grader. Okay. Procedure. Briefly describe the setup. Something about the apparatus and a string and ball and weight deal. Okay. Which tool to measure which variable? Okay. So there's only a handful of measuring tools, and I'm going to be using the relevant ones. Okay. Right. Okay. What's the independent variable, dependent variable, controls? You guys know AP always awards a point for multiple trials to reduce experimental uncertainty. Because the way we're going to do multiple trials, I'm going to touch this one a little bit. I'm going to grab 3 different times from you guys. So you guys each have stopwatches. So I'm going to get 3 volunteers. You guys tell me the times, and we'll make believe that that's 3 separate times, just because we've got so much class time. Okay. Analysis. I have a big old graph set up for you guys. You guys see this big old graph space? Okay. And there might be a little bit of calculations leading into that. Well, I had to calculate this to be able to get to that point. Maybe that's part of analysis. Okay. And then make sure your conclusion answers the question. And you guys know what the question is. What's the rotational inertia about the central axis? Okay, good so far? It's good? Okay. All right. All right. Let's see. How about volunteers with the stopwatch? All right. So who's volunteering for stopwatch? All right. So I got Joseph. I got who else wants to volunteer? Stopwatch. I got Isaac and Asher. All right. Here's my three stopwatch volunteers. All right. So let me get my camera switched over. Okay. All right. So here, so everybody knows the camera is back aimed toward this setup. Let me double check, make sure it's on frame. I think it is. Oh, hold on. Hold on. The top of this thing. Is that? Trying to make sure. Okay, is this going to be in frame? I had this in frame this morning. It's this bit right here. Oh, okay. I think that's just in frame right there. Okay, I think we're good. All right. So you guys see I have this string looped around, and then it's over this pulley, and then I can hang a lab weight right down here. It's gonna fall down. Like I said. Right? Like I said. All right. So say on this lab table, let me double check, make sure we got everything we can get so far. Look over here. Okay, we're doing what? Okay, what's the radius of that central axis? Right, so I'm going to measure this with the ruler right now. I think it's like a centimeter. Maybe I'll get the diameter and divide by 2. Yeah, the diameter is like 2.2 centimeters. Okay, so the diameter is 2.2 centimeters. Is the radius 1.1 centimeters? And that would be how many meters? 0.011. Okay, 0.011 meters radius. Right. Right. Then I'm gonna, and that'll actually be true all the way down the page. Right. So you just copy and paste that all the way down. Right. So what is the mass that I'm gonna hang on there? Now this I'm gonna treat sort of as an independent variable. Maybe I'll write IV above that second column, independent variable. So I'm gonna change that throughout the class period. Hang different lab weights. Right. What's the distance that it's gonna fall? Right. The distance, the falling distance to the ground. Right. So what else I got? Okay, that in time. I'm gonna switch my camera back over. All right, switch back over here. Okay. So what is this falling distance right here? Looks about 70 centimeters because I'm gonna hang the weight like right here at the 70 mark, and it's gonna go all the way to the ground. Okay. So yeah, 70 centimeters. How many meters is that? 0.70. Right. Actually, that'll probably be the same all the way down. Also, I mean, I don't see any reason to really change that. Okay. So that could be. Right. All right. Hey, you guys ready to time this? I got to pick a lab weight. Oops. All right, lab weight. Let's go. How about how about 50 grams? All right, 50 grams. So could that be how many kilograms?
0.05 kilograms.
Yeah, 0.050 there, kilograms. Okay. So that's the first lab weight. Okay. All right. Okay. All right, you guys ready with the stopwatches? Ready with the stopwatches? Okay. All right, so hang the slab weight on right here. Okay, so here's what I'm doing. I'm hanging a lab, or maybe we'll do a trial run with you guys so you guys can see exactly what's going on. Okay, I hang that lab weight. Oh, actually, what? Yeah, I forgot about this. Okay, that's not quite enough. There's a little bit of friction here, so the 50 is a little bit too small. Let's switch that to 100. Okay, all right, watch this thing fall. That's okay. It'll show up in the graph. You guys will see how that'll show up in the graph. Okay, guys, when I let that go, you guys see it's starting to spin. Right. And it's going to take some time for that to reach. Actually, that's a little bit small, isn't it, too? Okay. Let's bring it up to 150, actually. Let's try 150. Because it has to overcome a little bit of friction. Right. Hey, yeah, you guys see it spinning like that? It's going to take some time for those lab weights to hit the floor, won't it? Right. Guys, are those lab weights accelerating towards the floor? Yeah. And does that go hand in hand with, is this speeding up spinning? Is that an angular acceleration? You guys see that too? It's kind of subtle, but you can kind of tell it's going a little faster, a little faster. You see that? Right? Right. So how much time does that take to hit the floor? And then this turns into, okay, well, there's a kinematic aspect. It's if I know the distance it fell, and how much time starting from rest. That sounds like three kinematic variables. There's enough information there. You could calculate the linear acceleration of those lab weights falling. Right, you guys get that? Okay. And they're almost at the floor. So if you were timing it, then you'd be getting ready to stop it, right? But we're gonna just go back into this real. That was a little trial run, so you can see exactly what that looks like. Right, gonna rewind this thing. Right, and let this fall the full 70 centimeters starting from rest. All right, so start this up here. It's gonna fall 70 centimeters. All right, guys ready with the stopwatch? All right, ready? All right, ready, and go. All right, so while this is in process, because it's going to take some time, right? Let's think about that kinematic formula, guys. Which kinematic formula could you use to solve for acceleration? The first one. You guys remember x equals v naught t plus half at squared? Okay. Now starting from rest, the v naught t bit goes away, so it just boils down to x equals 1/2 at squared. Right? X is, well, that's the 0.7 meters. It's going to fall. It's doing right now. Right? The t we're about to get because we got some stopwatches going. Right? Right. So we'll be able to calculate the linear acceleration, and then that's going to kick off a whole process. Right? All right, ready? And stop. All right, so I got some times going. All right, let's flip the screen back over here. Boink. Right. I'm going to switch the mass to 0.150 because I forgot. Yeah, it's a little bit of friction it has to overcome. So it's kind of the minimum I could do. Okay, so we got 0.15 kilograms mass. Okay. All right. Joseph, what'd you get for you? Oh, yeah, what'd you get for your time?
We got 51.47 seconds.
51.47.
Yep.
All right. Isaac, what'd you get?
51.43.
51.43. All right, and Asher, what'd you get? 51.31. Oh man, those are all like exactly the same. All right, it's crazy. Okay, so acceleration. And now here's what I was just saying, or what we were just walking through with acceleration. The full formula x equals v naught t plus 1/2 at squared. Okay. You guys definitely have those three kinematic formulas memorized by now. Right, it would definitely be helpful. This v naught t goes away, starts from rest. Okay, hang on, got to get a page up here. Okay. So then we can solve for this linear acceleration. You guys got that? Okay. So it fell 0.70 meters. And it took, well, I guess you could do these individually. Maybe I'll do one of them with you guys because they're all about the same anyway. Okay, let's do 51.47. So if I do 51.47 seconds and then square that like that. Okay. So you guys could do some algebra. It looks like 2 times the distance divided by the time squared, which by the way, I wrote right there, or I typed it right there. Is that 2x over t squared? Okay. Which you guys have seen before. Okay. I remember one place you saw it was Atwood's. In Atwood's, I wrote that little expression, and here's where it comes from. Here's if you plug the numbers in first. So 0.7 times 2 divided by 7 squared. I'm getting the linear acceleration was 0.00053 meters per second squared. Yeah, which I think makes about sense because it was accelerating so slowly. It took a long time to fall 70 centimeters. Okay? I mean, it was accelerating just extremely slowly. Okay? So that looks like this number right here, 0.00053. That's meters per second squared. Okay. All right, guys good? All right, next column. What is the tension in the string? Because that tension is the force that's providing the torque. Okay. Now, I think really that tension, it was accelerating so slowly, you could probably just call it the weight. And AP might even do that. They might just kind of make a little simplification. Okay. But if you do it properly, or if it was accelerating so much that it was significantly less than the weight. Do you guys remember elevator physics? We draw the free body diagram here. I'm going to exaggerate this a little bit. If you got the weight down, and I'll call it T for tension, up, okay, then what does this look like? I got net force, so sum of forces equals mass times acceleration. Okay. The net force would be the weight down minus the tension up, okay, which ultimately we want to solve for. Okay. That results in mass times acceleration. Okay. Okay. Skip a couple algebra steps here. Tension equals m times g minus a. All right, you guys see that? Okay. Which I also typed right there. You guys see m times g minus a? Okay. So this is where it comes from. And to be ready to do this, I mean, this could totally be a big part of an AP free response question. Right? They might expect you to solve this from scratch, exactly like I just did it. Okay. Right. Now, since this A is so small compared to the G, then again, if you forgot this step, then it's pretty close to the weight anyway. The tension is right. Let's try that. So yeah, 0.15 kilograms times 9.8 meters per second squared here, minus the 0.00053 meters per second that's actually accelerating down. We get like 1.47 newtons. 1.47 newtons. Okay, you guys get that? Okay, you guys good? Okay. Then turntable physics. You guys remember if there's a turntable? I had a poster that said how far it turns is equal to theta times r, as in circumference equals 2 pi r is a version of that. V equals omega times r, and A equals alpha times r. And if you play out that last one, you can rearrange and get alpha equals A divided by r. You guys remember that turntable physics? Right? So a little tiny cross section of a circle. That's what that is right there, A over r. So I'm going to take this A, which is 0.00053 meters per second squared, divide by the radial size, which was 0.011 meters, right? You guys good so far where all these are coming from? Okay. And what does this tell me? Is 0.048, 0.048. Guys, what's the units on that? That's 0.048 what? Radians per second squared, exactly, because it's an angular acceleration. Radians per second squared. Something to do with it speeding up spinning. Okay. All right. Torque. Well, I remember torque was R cross F right here. So if torque was R cross F, okay, and I know the radius is 0.011 meters. I know the force, right, which we just found over here is the tension. That's 1.47 newtons, right here. Right? And conveniently for this type setup, because whenever you wind a string around a turntable, it's really hard to not pull it at 90 degrees. Let me find a blown up picture of what I'm talking about.
What'd you get for the meters per second again?
Oh, okay. Do you want the acceleration in meters per second squared?
Yeah, for the acceleration.
I got 0.00053 meters per second squared. And the angular acceleration alpha is 0.048. And that's radians per second squared.
Thank you.
Okay. All right. So let's find here. This one. Okay, see, isn't this basically a little cross section of what's one? There's a string wrapped around that central pipe. Looks like about like this. Okay. Because no matter how you pull the string, isn't the string tension always going to be perpendicular to the radial arm from the center? Yeah. Okay. So very conveniently, the cross product is always maximized. So okay, so that's nice. Okay. So all I got to do is just make this product right here. 0.011 times 1.47 gives me 0.016 Newton meters of torque. 0.016 Newton meters of torque. Right? Guess yet? That's good. Okay. Everybody doing all right? All right. All right. All right. Do you guys think you can do those other calculations and figure out the average values there? Guess yet? Okay. All right. Guys, good so far. Good so far. Okay. All right. And we'll consider that 3 trials for that's going to give us one average point on this graph, Cartesian coordinate somewhere. All right. So now what I do is just change out this mass right here. Okay. So it's going to be the same radial size all the way down. Okay. What if I bump this up to 200 grams, 0.200? Okay. Let's do this. What if it's 0.30? What if it's 0.40? What if it's 0.50? Those are probably some good numbers, right? 0.2, 0.3, 0.4, 0.5. Okay. Kilograms. Okay. All right. I think that'll finish this out. All right, so I just switched my screen back over to this lab setup. All right, gonna rewind this. All right, you guys are doing some calculations, and if you're finished with the calculations, then what was what here? If you're finished with the calculations, see if you can make some progress on that lab write-up, write some procedure stuff. All right. All right, so I need 200 grams. Well, conveniently, there is a 200-gram lab mass right here. All right, so got 200 grams. All right, guys ready to go with 200 grams? So right here, 200 grams. All right, got all the stopwatches ready?
Yep.
All right, ready, and go. Okay, we're gonna start that over. Sorry about that. Yeah, you guys can make some calculations as we're going along because it's gonna take some time for this to play out. All right, let's start over. Here we go. And oh, whoops. All right, thanks.
I am ready.
All right, and go. I think it's going a little faster than before. Right? Probably makes sense. Okay, and stop. All right.
I stopped it as soon as I hit the ground.
Push this back over here. All right, so just what are you getting on that time?
For the time, I got 29 seconds.
29 seconds? All right. How about Isaac?
29.44.
29.44? Right. Asher. 29 point what? 9? All right. Right. Okay. That was the same falling distance, 0.70 meters. Okay. You guys think you can do the calculations and figure out what was the torque? Is it? By an average value? Yeah. All right. All right. So while you guys are doing these calculations, I'm gonna rewind this thing over here. It's all set up. All right. All right. So next we're going for 0.30 kilograms. Switch screen. Okay, back over here. So we got 200 grams and 100 grams. If I put those on, that's 300 grams, which is next trial we're looking for. So 300 grams right here. All right, you guys ready with stopwatches? All right, and go. Okay, and stop. All right. Here. All right, so Joseph, what time did you get?
I got 19.5 at 57.
1957. All right. Oh, I said
20.15.
20.15.
15.
Yeah, 20, you said 20.15.
Yeah.
Okay. And Asher, 20.19. Ooh, all right, pretty good. All right, you guys got some calculations to do. I'm gonna rewind this system. There. Okay, so next one, we're doing 400 grams. All right, so So here first, 400 grams. Boink. Boink. All right. Switch my screen over. Back over here. Try to run away. Get back here. All right, you guys ready for stopwatches? All right, ready and go. And stop. All right, so same distance as before. Now we got 400 grams. Just a foot time.
I got 16.68.
16.68. Isaac, 1675. And Asher, 1684. Oh man, you guys' times are all like about the same. Great how close that is. All right. Okay. So last one is going to be half a kilogram. Gonna rewind this thing. All you guys do is some calculations. Hit this reset. All right, got 500 grams right here. Let's over. Let's set up. Sure. Okay. Back over here. All right, guys, ready with stopwatches? Stopwatches. All right, so 500 grams. All right, ready and go. And stop. All right, so that's all right, Joseph, how much time?
14.28.
14.28. Isaac,
14,
1418, and Asher, 14.28. Crazy. All right. Let's get some average. So somebody have some average values calculated for all these. So average, you can add them up and divide by 3, right? Anybody got these boxes? How about this? Let's do this. Since we got just about 3 minutes of class left, go ahead and do as many calculations as you can. Now, these 2 bold boxes here at the bottom of each trial, do you guys see these are going to be Cartesian coordinates on this graph? Right? So I got average alpha and average tau. Here's alpha on the x-axis. Here's tau on the y-axis. Right? Guys, what shape do you think this graph is going to look like? You think linear? Right? I think linear also because tau equals I alpha. Right? Tau equals I times alpha. Okay. Now there might be an intercept also because I remember. Well, maybe I'll leave that as an open question as to if there is an intercept, what would that possibly represent? Right? But I bet those points line up in a straight line. Okay. So I think we'll have to do this. Guys, come to class tomorrow with this data calculated. We'll put the graph together, and guys also have a procedure written because I do have an AP rubric write-up. Right. Oh, here. Okay. Got this rotational inertia lab write-up. Okay. So yeah, what's the question, which I did with you guys? What's the measuring tools? You guys have some measuring tools you guys figure out what we use. Data gathering procedure. I have what, about 6 points right there. Okay. What's the analysis? So I got a few equations and graph properties, and then we're going to get a conclusion. So we'll have to finish this lab tomorrow. I'll go over the scoring rubric with you guys for the write-up. Oh, yeah. For what?
Like, I'm not gonna get an answer.
Oh,
It's just, I'm reading.
yeah, R times T. So 0.011 times tension of 1.47. Yeah, you just did this R times this tension. Got this torque. All right.
We got it.
All right. Yeah, so we will finish this tomorrow.
Alex, bro, stop the car.